Okay, so we continue with our discussion of diffusion models, and we move on to talk about the actual implementations or the different ways of considering the probability flow, the um, improvement on DDPM, which is called DDIM, implicit models, and consistency. So this would kind of like bring things together into practical applications. So what is DDIM and consistency? So DDIM, which is the denoising implicit models, um, and they're developed as an improvement upon DDPMs. Where the advantages is to try kind of to leverage on the ordinary differential equations formalism, and by doing this, achieve less samples, less steps, and it also introduces the idea of sample consistency, which means that you want to generate samples, which, when you start from same initial latent state, regardless of the sampling trajectory, you'll arrive at the same solution. And it also has some other advantages like interpolation and reconstruction. So, of course, looking into the original DDIM paper is full of these important details that we will not really cover, but I kind of summarize this in this slide. So, what actually is going on? So basically, if we go back to the SDE formalism, we have seen that we can start with some kind of distribution of the original data, and then by going through this Wiener process or the diffusion process, we smear this into basically noise like a Gaussian, which kind of loses in practice all the information that was about the original distribution. But if we do know the score function, we can go back and reconstruct new samples. So the whole secret is really this score function estimation. Now, if we want to go and use the ODE, we can reverse that probability using ODE, and we showed this example in the previous notebook. And this way we can kind of go and use deterministic process. And again, they both use the same score function. So this idea, I think we kind of described over and over, where kind of the notion of having a difference between models which are stochastic, which are flow models that incorporate the whole process of adding and diffusion, starting from some initial model, you actually arrive at different latent states. While here in the ODE model, we have actually one function that maps everything to the same variable, and it uses uses the score function. Now, we did go through this DDIM example in the previous recording, so I will not repeat it here. But I think kind of brings together all these concepts into this idea of consistency. So we said that diffusion model sampling takes a lot of steps. So even with some of the advanced sampling techniques, there's still a lot of steps required. So what consistency models try to do is basically address this idea that when you go from your original data to any of these denoise versions, you can actually try to calculate different recovery or different reconstruction functions, and you want to make sure that they all land in the same data point. And the advantage and disadvantage is that now you can do this. If you find these functions, you can do this in one step, but you will be always recovering the same data point. So they're basically trying to generate samples, okay? in a single step, and they need to satisfy multiple properties. And these properties, as we have seen before, that from all points along this trajectory, we have a function that actually recovers the same initial data. So they're trained to map points on any trajectory of the ODE to the same starting point. And also, it uses a specific kind of network parameterization condition, a boundary condition, that basically combines this with this self-consistency. So the consistency really is the fact that for any t, you get the same function that actually maps everything together. So we won't get too deep into consistency. I kind of wanted to introduce this concept and kind of summarize. So this section is really more of a summary of a lot of concepts that now are present. Now, a good paper that kind of brings everything together. It's quite a voluminous paper with a lot of details, especially the appendices kind of repeat a lot of the theory. And it's the EDM paper, the Elucidating Design Space of Diffusion Models. And what they do is basically suggest that the training and the sampling should be separated. You can treat them separately. And you might consider specific regimes for the noise in terms of the sampling, going back, and also adding noise when you go forward in the training. And it explores a lot of design choices. Okay, let's jump to the next slide, because they kind of define several families, if you want to say, of these possible diffusion models. One they call variance preserving. Another one is variance exploding, and another one is actually a specific noise schedule, including the possibility of using so-called distillation or teacher and student model to train a more efficient inference model after we have trained with a lot of steps a diffusion model like DDPM. So what are these variance preserving and variance exploding models? So they all follow the same SDE kind of framework, where the variance exploding is really the more intuitive, just adding diffusion at every step. So we don't have any of the original data. But like in the variance preserving, we do have our original data here, while in the variance exploding, all we do is just move towards the noise, where this is the winner process, the capital DW, and this is how the trajectory is shifted. While so the problem is that to arrive at the fully kind of like random state after these steps of diffusion, and T can be very large, you keep increasing this variance, the sigma, and that's why the variance is exploding, because you want noise to cover your original starting point with infinite amount of noise. While the variance preserving model is actually introducing this kind of a scaling factor here that takes the original data and kind of fades it out. So this is a scaling factor that at every step introduces less noise, because it also keeps the original data, but it adds basically that data with a fading out function, basically. So this model preserves the variance, and apparently this is a more efficient way to train the models. And the last one I mentioned is, well, finding the right schedules using specific ranges of these noises. A quite elaborate paper. I just wanted to mention here for anyone who's interested in trying kind of to look into state-of-the-art actually techniques for using diffusion in an efficient manner. So let me kind of try to summarize what we had so far. We introduced a general stochastic differential equation as this extension to a normal differential equation. This would be, this left part here. I hope you can follow my cursor. is what a usual derivative would be. Okay, dx dt is f of x. F of x is some kind of derivative of the function. So there is another function which is the integral. So f is the derivative of some other function, and this is, if you want to think about a dynamic process as a differential equation, this actually defines the dynamics. In the case of diffusion models, this whole kind of dispersion, the Wiener processes, we have this additional element here, which creates this random walk. And at every step, we actually add noise as we progress through the original dynamics with additional shift. Now, in order to analyze, and this is what a lot of the theory in these papers kind of gives, actually presents and assumes, it gives it for granted. They mention these Fokker-Planck equations, which need to be actually explained using so-called Ito calculus that tells us that, a probability, okay, if we think now about a random process, how this random process evolves in time. And this is the derivative, the change in the random process. It's not only the change in the dynamics, but it also adds this extra component related to the scale of the noise that we add. And this is specific factor half g square, which comes from that Ito calculus. I'll upload a separate set of notes on the website. I will not cover them in the lecture. That kind of derives the Fokker-Planck equations from the basic Ito derivative. And Ito derivative actually shows us that, when you add a noise, the derivative, which is a slope of a function at a certain point, is actually shifted by adding noise. So you're not staying in the same point on your curve, but the noise basically throws you out of the minimum. And then what you actually have to account is for the curvature. So I was kind of thinking maybe about demonstrating this, but physically, but I didn't bring it. But you can imagine, let's say you have some kind of a ball, and you have a little ball that kind of resides in that ball, and that little pin, okay, when it sits at the bottom of that ball, it will be at the extrema, okay, and then the curve is zero. But if you constantly jitter that ball, basically make that little ball jump up and down on the curve, the slope actually of that function, if you consider the noise, will be higher. It will be basically covering not the original point, but the margins a little bit higher because of the temperature, the jitter. So what we have is actually this expression that has this Laplacian, or the second derivative. Again, maybe the math is too much for the purpose of just describing the techniques, but given these equations, the whole idea of reverse time is creating another dynamics that basically inverses the sign. Okay, so we now want to go back with the probability from pure noise to our let's say bimodal distribution. Okay, so if we had a process that took us from the bimodal distribution to just a Gaussian, then we want to go from Gaussian back to bimodal distribution with an inverting this process. Now, when we invert this process, we invert the sign here, but it still adds this jitter because we go back with a random process. So if you follow the math in these extra slides or in the papers, basically these two add together. That's why you get a G and not half a G square. And you get this new dynamic process that actually reverses the dynamics. So if this is the forward process, this becomes the inverse SDE. And that allows us to go and simulate back the situation. Now, the whole yeah, so this is kind of the same thing written here, okay, where we kind of want to remove the noise. But if you repeat the same logic of the Fokker-Plaquemine equations, but you don't go back with the noise, you don't have this extra half factor. So you have this ODE reversal, which is slightly different. So you see, we have two versions here. Okay, one is going back with a random process, a stochastic process, and this is what DDPM does. Okay, or you can go with a deterministic process with the ODE. It doesn't have this jitter component, and it actually has a half here instead of GT square here. So little details, but when you look at these equations and you jump between all of these solutions, you might wonder why the equations look differently, even if you didn't know the derivation. So I hope, this kind of gives you an overall idea and this intuition about what is the difference between going randomly from structure to no from random. Well, I mean, your data itself is a distribution, but you go from some kind of a structured distribution to a very unstructured distribution, or kind of pure randomness, and then going back. And if you go back with, again, a random process, you follow these equations, and that's where you have this extra sampling in the DDPM. You add noise every step, and I think that's a little bit counterintuitive, but this is what the math requires. Or if you do DDIM, you can follow these equations in a more deterministic way. So we are still left with these questions with the question, well, how do we find the score? Okay. We already spent an hour trying kind of to explain the whole idea that score can be used to generate your probability. If you know it, we showed these ideas of going back and forth, so you can basically reverse the process. But I mean, how do you know? How do you know which way to go? How do you know this score function? So in this case, it kind of helps to look into, I would say, the original or one of the establishing methods of using score and estimating score instead of using so-called, we did maximum likelihood every time we use maximum likelihood, right? Also, we maximize the probability or the likelihood of probability when we use the elbow. But here, it's kind of an alternative approach. Instead of learning a probability, we learn the score. I've repeated this many times. But now, how do you learn the score? So for the purpose of kind of motivating this a little bit further, I have this little collab simulation that I will show. And what it does, it actually uses the DSM laws by Vincent from an earlier paper, where the whole idea is that, okay, now we want to learn the score. Now, how do you learn the score? Well, we don't know the original probability. We don't know the gradient of that probability, but we can use a specific formalism. And that kind of comes from a formula called Tweedy's formula that I'll kind of just motivate it here. I will not go through every detail, although I think it's pretty straightforward. It's calculus. So I invite you kind of to follow it. So what we have is basically the idea that we have, our initial probability X, and we don't know what it is, but we can sample from it. But since we don't know, we don't have the analytical expression, we don't know how to calculate the gradient of the log or the score function. And if you recall the previous simulations, we actually did that analytically. Now, if all we can do is empirically sample from the data, what Vincent paper proposes is actually to do the following. You actually take your samples, which are the X, that's your original data, and you deliberately add noise, okay? Now, if you deliberately add noise, following all of these derivations with the Bayesian formula, and if you add noise as a Gaussian, so you know what noise you added, you can kind of go and can calculate the posterior. You can derive the gradient of the posterior of y, okay? And that's the conditional one, okay? So the conditional one, you know how it looks like. Now you can calculate, you know, the conditional, right? So because the conditional is the noise you added. So if you know what's the x, you know what is the probability of y of x, y given x, that's the noise you added. You can use, as we said, base, still to use the same expression here, the px shifts goes to the other side. And then going further, you can actually calculate the score function of the noisy version of your data. Now, if you do that and you follow a couple more steps, you actually arrive at what's called the Tweedy formula, okay? Or what we use is kind of one step before the Tweedy formula that gives you this score. So what is the score? Score becomes actually the mean of your data given the noised version minus the noised version, okay? So if you kind of like translate it to here, okay, basically what we have now a neural network S that tries to model or approximate our score function. Instead of score function, which is the original score function, we want to estimate the score function of the noisy data, the noisy distribution. And giving that, this is your noisy distribution, and using this formula, you know, here's the x and y are kind of inverted. And so this way you have, it's plus here, or it's x minus x, which is the noisy sample. So for every sample, you take its noisy version, you subtract, you divide by sigma square, and you repeat this. So you average this on all points, and a lot of noise instances. And by now using this loss function as a training loss in your neural network, you are actually going to be able to estimate your score and then use the score to denoise. Okay, so at this point in time, okay, after we already talked a lot about all of the mathematical theory, I want to show you how actually we can go now back from noisy data or from noisy data back to the original data using this trick. So this is the first time we're actually going to show you how we can estimate the score function. So let's open the Colab. Okay, so so basically what we have is, oh, sorry, let me close some sessions. Okay, so what we have here is, okay, initializing this whole thing. We'll generate sample data, which is going to be our original distribution. So don't be confused. We are also generating our data from a random probability because that's the probability we want to learn. And then we'll add another layer of noise in order to be able to learn that probability. Okay, so even though we know here analytically what we generated, we sort of like treat this now as just samples from the real world. So these are the samples we generate. We generate these two Gaussians here, okay? And now we want to learn them, okay? So how we do that? We actually add noise to corrupt the original samples. So you see, so now the yellow ones are the original data, and now we extended them by adding noise around every sample we took. Okay, so if this was -4 to 4, you can see that this one kind of is expanded. We added noise. So don't be confused because they still look the same. But you know, this was our original distribution, very centered. Now we kind of spread it out using additional noise. Now the next step is actually to create a neural network that will learn the score function of the noisy distribution. Okay, so in this case, we kind of create this 3 layers of sequential ReLU network. we start with 2 dimensions, we expand it to 64, then we go from 64 back to 2. And this is going to be our approximation for basically the score, the gradient of the log. Okay, this is our model. Okay, so once we define that, we go and we run this whole simulation. So what is that simulation? Okay, we have our loss, DSM loss, just from the equation we showed before, the score minus the target, and the target is that x tilde minus x divided by sigma square, exactly that equation. It's actually with a minus, and then minus with the minus makes plus. So if you look this up in comparison to the slides, they're inverted there because the minus and minus is giving you the plus. And then we can just train it. So if we go ahead and train this by taking every sample from our original distribution, adding noise, and then calculating, a score where we actually want to minimize this loss, okay, we converge into a network that now we can see what it does. Okay, so what this network does, it actually takes every point and predicts which direction to go because it's the gradient. Okay, so you can see that we managed to learn the score. Okay, we managed to now have this vector field, and then if you now sample this and follow this field, you can actually recreate the original distribution. So I think it's pretty amazing because that's what we actually do to learn the original distribution. We learn this distribution by adding an extra noise and denoising it, and by finding which way we should denoise it, we actually find how to simulate the original data. Now, it is sensitive to the amount of noise. So, of course, if you add too much noise, you will not be able to kind of go correctly. So if instead of sigma 0.5, I know I just take sigma 5, okay? And that means I add a lot of noise, okay? You can imagine that, I can try to train, it's the same network, I can try to train it again, and you'll see that, it does converge, it does find directions, but if we look at the eventual vector field, okay, let me just finish this. Yeah, you see, it didn't manage to find anything. It just basically learned the original distribution. So this is why you need sufficiently small amount of noise. If I don't go with 5, we had 0.5. If I go with, I don't know, let's say 2.5, okay, it might still work because it still kind of maintains a little bit of the original structure. It's not all hidden in noise. And then I can try to learn it again. And it's kind of a fun thing. Try this out, play around with this notebook, because it gives you this notion of, when this kind of a diffusion score matching method starts breaking apart. So you see, it kind of did something, but it kind of didn't really learn that you have to go this way. It just kind of, well, it will approximate something, but it will not be the right distribution of the two Gaussians really centered here, kind of spreads them out. Yeah, so let me go back to the slides. I think this kind of summarizes the whole idea of, switching from maximum likelihood to score matching, the math behind it, the idea that you can learn instead of the probability, you can learn the score function, and yeah, and that's it. So I'll stop the recording before I move on to the next set of slides.